Hello and welcome to my lesson on the Pigeonhole Principle. So, the Pigeonhole Principle is actually quite simple, and it states that if you have n boxes and n plus 1 pigeons, then if you were to put the pigeons in the boxes, at least 2 pigeons would be sharing a box. So for example, if I have 3 boxes and I wanted to put 4 pigeons in either of these boxes, so I'll just represent a pigeon by a dot. So I could put one in each, like such. However, the fourth one would have to go into one of these holes, and since all of these holes already have a pigeon, the 2 pigeons must share a hole, no matter what. Okay, so the first question is, if a Martian has an infinite number of red, blue, yellow and black socks in a drawer, how many socks must the Martian pull out of the drawer to guarantee that he has a pair? Okay, so I know it says black socks, but I'm just going to use green instead. So the first thing to do in these Pigeonhole Principle questions is to decide what you're going to make your pigeonholes and what you are going to make your pigeons. The only way to get better at this is to do more questions. So this is quite an easy question in the sense that it's simple to identify what we should make our pigeons and what we should make our pigeonholes. So obviously we should make our pigeonholes the 4 different colours. So red, blue, yellow and black. So if I just draw the pigeonholes, we have a red one, blue one, a yellow one, and we have a green one. Okay, so these are our 4 different pigeonholes. In order to get 2 pigeons to share a hole, then we need at least n plus 1 pigeons, where n is the number of pigeonholes. So since we have 4 pigeonholes, to guarantee that 2 pigeons, which in this case will obviously be the socks, in order to ensure that 2 socks share the same colour, then clearly we need to have 5 socks because it's 1 more than the number of pigeonholes. So this is quite easy to show because we could have 1 red one, 1 blue one, 1 yellow one, and then 1 green one. And then if we wanted to pick another sock, it must be one of these 4 colours, and so we must thus have 2 socks that are of 1 colour. Okay, so the next question is that 6 distinct positive integers are randomly chosen between 1 and 2006 inclusive. What is the probability that some pair of these integers has a difference that is a multiple of 5? So this question is more difficult than the first one in the sense that it's harder to identify what we should make our pigeonholes and what we should make our pigeons. So with this question, we can try to find a pattern that must be present in order for 2 numbers to have a difference as a multiple of 5. So let's take any 2 numbers that have a difference as a multiple of 5. So for example, we could have 27 and we could have 12, so 27 minus 12, and their difference is 15. So what do 27 and 12 have in common? Well, if you think about it, 27 and 12 have the same remainder when divided by 5, as 27 is equal to 5 times 5 plus 2, and 12 is equal to 5 times 2 plus 2. And so clearly they both have a remainder of 2. So then from this we can start to suggest that in order for the difference of 2 numbers to be a multiple of 5, they must have the same remainder when divided by 5. And we might like to try a different pair of numbers, so we could try, maybe we could try 18 and maybe 8. So obviously the difference is 10, and we can see that 18 divided by 5 is 3 remainder 3, and 8 divided by 5 is 1 remainder 3. And so clearly they have the same remainder when divided by 5, and the difference is a multiple of 5 as well. So once you've realised that the two numbers that you're using as the to do the subtraction must have the same remainder when divided by 5, you can then proceed to apply the pigeonhole principle. But before that, I'm just going to quickly prove that the two numbers must have the same remainder when divided by 5 in order to have a difference that is a multiple of 5. So let's say I have two numbers, and we'll call them x and y, and their difference will be 5n, and x and y and n are positive integers, and without loss of generality, we'll just say that x is greater than or equal to y. Okay, so to carry on with the proof, we will need to rewrite x and y. So we'll say x is equal to 5a plus b. Any integer can be written in this form, and so a and b are, a is the quotient when x is divided by 5, and b is the remainder when x is divided by 5. And we can then rewrite y as 5c plus d, where again c is the quotient when y is divided by 5, and d is the remainder. And because x is greater than or equal to y, we can say that a is greater than or equal to c, and we can also say that because b and d are the remainders when x and y are divided by 5, we can say that b and d are greater than or equal to 0 and less than or equal to 4. So if we substitute 5a plus b and 5c plus d back into our original equation here, we will get 5a plus b minus 5c minus d is equal to 5n. And so if we then divide both equations by 5, we will get a plus b over 5 minus c minus d over 5 is equal to n. And so a minus c plus b over 5 minus d over 5 is equal to n. And so because a is greater than or equal to c, we know that a minus c must be greater than or equal to 0. And we also know that n is a positive integer, and so, or actually it could be 0 as well. And this means that in order for this equation to hold, where a, c, b, d, and n are positive integers and 0, b over 5 minus d over 5 must be an integer greater than or equal to 0. And so if we consider the maximum value of this expression in this bracket here, we can see that if we let b equal to 4 and d equal to 0, then we'll get 4/5 minus 0 over 5, which is obviously equal to 4/5. And so the maximum value of this bracket is 4 over 5. However, we need the value of this bracket to be an integer. And so we can thus deduce that this bracket here must be equal to 0 in order for this equation here to work. And so b minus b over 5 minus d over 5 must be equal to 0, and so b must be equal to d. Okay, so I've just proved that now, and so I'm just going to quickly rub all this out, and we're going to go back and apply our pigeonhole principle. Okay, so now we have to decide what are we going to make our pigeonholes, and what are we going to make our pigeons. So let's start with the pigeonholes, because I always believe that it's better to start with the pigeonholes. So if we have our pigeonholes, so we have to consider the remainders. And for this question, after thinking for some time, you should realize that the best thing to do is to make the remainders of numbers when divided by 5 the pigeonholes. Okay, what do I mean by that? So if we divide something by 5, there are obviously only 5 different possible remainders, they are 0 if it is a multiple of 5, 1 if it's 1 greater than a multiple of 5, and then 2, 3, and 4. Notice that a remainder of 5 is the same as a remainder of 0. Okay, so now we've made these 5 remainders our pigeonholes, and we want to choose 6 different positive integers, which are our pigeons. And so because we have 6 pigeons and for only 5 pigeonholes, by the pigeonhole principle, 2 of these 6 different positive integers must share a pigeonhole, which are the remainders. So that means that 2 of the positive integers in the list of 6 must have the same remainder, and so therefore the probability that 2 positive integers in that list have a difference as a multiple of 5 is actually 1. You will always find 2 positive integers that have a difference that is a multiple of 5 if you choose 6 different positive integers. And that doesn't matter whether it's between 1 and 2006 or 1 in a million. The probability is always 1. Okay, so the next question asks us to consider any 5 points P1 to P5 in the interior of a square S of side length 1. Show that one can find 2 of the points at distance at most root 2 over 2 apart. So I've drawn square S here, and these questions come up a lot, like these like variations on this style of questions where you have points inside a shape and you have to prove that 2 points are at most root 2 over 2 at any distance apart. And once you know how to solve them, they're really easy to solve. So with these type of questions, the pigeon will always be the point. So in this case, the 5 points inside the square. And so if we have 5 points and we want to apply the pigeonhole principle, then clearly we're going to want to have 4 pigeonholes. And so to create our pigeonholes, we will want to divide this square into 4 equal areas. And so we can do that by drawing 2 lines as such. So joining just like that, and obviously these points here will be the midpoints of the side of the square, and so each square will have a side length of half. So if I write half and half. So now let's consider one of these squares. So if we were to choose any 2 points in this square, what would be the maximum distance that they could be apart? Well, the maximum distance would be if one was at one corner, such as here, and the other one was along the diagonal and all the way on the other side here. So by Pythagoras Theorem, we can work out the length of this diagonal here, and it will be the square root of a half squared plus a half squared, which will be equal to the square root of half, which is then equal to 1 over root 2, which is then equal to root 2 divided by 2. Okay, so now we've worked out the diagonal. What do we do from here? Well, if we consider the 5 points, we have 4 different regions. So by the pigeonhole principle, 2 of the 5 points must be in the same region. So if we put one, this region here, one here, one here, and one here, our final 5th point must be in one of these 4 regions. And so because it's in one of these 4 regions, it will share a region with another point. And since the maximum distance between 2 points in a region is root 2 over 2, we have proved that one can find 2 points that are a distance of root 2 over 2 at most. Okay, so now let's look at the 4th question. So the 4th question states that every point in a plane is either red, green, or blue. Prove that there exists a rectangle in the plane such that all of its vertices are the same colour. So this question is definitely a very difficult one, and I must admit it did take me probably about an hour to solve. So I'm just going to present the solution, And so the trick is to consider a group of 4 collinear points, so 4 points that lie in a straight line. And so if we have 4 points and we make these our pigeons, and then we let the 3 different colours be our pigeonholes, then by the pigeonhole principle, at least 2 of those 4 points must be the same colour. So for example, we make the first point blue, and then we could have the second point blue as well, and then we could have the third point to be red, and then we could let the fourth point be green. This is just one example. There are obviously many combinations. The trick is to then consider how many different possibilities there are to colour these 4 different points. So if we consider the first point, there are 3 possible colours for it, so 3. There are then 3 possibilities for the colour of the second point, so we have to multiply by 3. And then for the third and fourth point, there are also 3 different possibilities, so we have to multiply by 3 twice. And thus this gives us 81 different combinations for the colour of these 4 points. And so if we then make the pigeonholes, the 81 different combinations, and we let a column of 4 points, so for example this here, these 4 points would be 1 pigeon, in order to ensure that we get 2 columns that are the same, we need 82 pigeons by the pigeonhole principle. So if we had 82 of these columns, where each point can be any one of those 3 columns, after the 81st one, so the 82nd one, that 82nd one must be a repeated pattern of 4 points, if you get what I mean. So the colouring of those 4 points on the 82nd one must be the same as a previous one. So without lots of generality, let's let the first repeated combination be these 4 points here. So if I just quickly draw them out again, you can see that we can form a rectangle where all the vertices are the same colour by connecting the 4 blue points. So for example, and so this is a rectangle with all of its vertices being the same colour, and thus we have proved that such a rectangle does exist.